Welcome back, ladies and gentlemen. Good morning, good afternoon, good evening. Whenever you are seeing this, you are invited to see the third part of the video on derivatives. If you remember last video, at the end of video numéro 2, we saw that if we took f of x is equal to 1 over x, we actually got, as a result for the derivative, through the limit definition, we got minus 1 over x squared. Today, I'd like to explore what happens when the derivative actually takes on specific points. For example, what is f prime of 0? Well, f prime of 0, very easy to compute because f prime is minus 1 over x squared, so it's minus 1 over 0 squared. And what is that? That's 1 over 0. So that's what we call deity, or undefined. Now, I'd like to investigate a little further why this is happening here. So consider the graph of f of x. Consider the graph of f of x is equal to 1 over x, right? The graph of the function that we actually found the derivative of late in the part 2 of derivative video. The graph actually, I think we all know this one, right? I think we all know this one. It's now at least a little bit famous. Looks like this. Sorry if it's not super smooth, but we all know the rational function. And what happens to this graph at x is equal to 0? When x is equal to 0, what do we have here? We have that f of x has a vertical asymptote. Has a vertical asymptote. Asymptote. Well, an asymptote is, as we saw before, a major cause of discontinuity, right? It's impossible to sketch the graph in orange without lifting the marker from the whiteboard. In other words, discontinuity in the sense of an asymptotic discontinuity at x is equal to 0 results in f prime of 0 not existing. Right? There's a definite connection between the fact that the graph is discontinuous at 0, in this case it's discontinuous because of an asymptote, and the fact that the derivative at that very point does not exist. We're going to see other situations where discontinuity and the derivative are actually sort of linked together. So before we do that, let's erase this and let us give a little bit of a quick definition. Let's give a quick definition. So we will say that f is, here's a new word, not discontinuous, sorry, is not differentiable, that is a mouthful, not differentiable, so that's our new term. If f prime does not exist at a certain point x equals a, say. So we're going to say that f is not differentiable here at x equals a if f prime does not exist. Example, f of x is equal to 1 over x is not differentiable at 0, is not differentiable at x is equal to 0, since the derivative of x evaluated at 0, so f prime of 0, is minus 1 over 0 squared, which does not exist. So f of x is not differentiable because the derivative does not exist. So the differentiability means actually the derivative exists. Not differentiable means the derivative does not exist. Okay, good. Let us take a look at, you know what, I'll need a lot of space for the next problem. So I'm going to erase this and start a new whiteboard in 2, 1, 0. Okay, so let's consider, I guess this is example 1 for today. Consider f of x is equal to the cube root of x. Question, is f of x differentiable at x is equal to 0? Okay, so are we differentiable at x is equal to 0? All right, this coffee is good. So, question mark. We need to find, to answer this question, we need to find the derivative of f. We need to find f prime of x, right? And then we need to replace x by 0 to see if f prime of 0 will exist. So let us find f prime of x. We have a definition. F prime of x is the limit as h goes to 0 of, I think we're starting to know this by now, fx plus h minus fx over h. So that's the limit as h goes to 0 of, let's start with the easy part, f of x. F of x is cube root of x. And then f of x plus h, well, that's also pretty easy. All we got to do is replace x with x plus h. Make sure it's inside the root, all over h. By now, I think you're starting to know that at this stage of the problem, if I replace h by 0, I am going to get 0 over 0. I do because x plus 0 is x. Cube root of x minus cube root of x is 0. And the bottom is 0. That doesn't look like it, but this is a very difficult limit to evaluate. Why? Because, well, the conjugate doesn't work on a cube root like this. We need to find another approach. And for that, I'm going to go aside. So I'm going to actually come back to this in a minute. So I'm going to write what I'm going to write. Okay? I'm going to come back to this. But I need to actually do a little bit of algebraic manipulation here. So first of all, a little quick recall before we go on. Maybe recall a3 minus b3. Difference of cubes. We've seen that before. Who remembers a3 minus b3? This is a minus b and a squared plus ab plus b squared. We're going to use that now because I'm going to pull a little bit of a stunt on you guys here. Look at this guy. Yay or nay? Is h the same thing as x minus h minus x? Would you agree? Oh, sorry, x plus h minus x. It wouldn't work otherwise. So if I remove the bracket, the x's cancel. I get h. Okay, so far, nothing fancy. But here's the fancy trick. I am going to write x plus h as, well, a very unusual thing. I'm going to put here the cube root of x plus h all cubed. Would you agree that if I cube a cube root, I'm going to get exactly what I started off with, which is x plus h. And I'm going to do the same thing here. So I'm going to do the cube root of x, and I am going to cube it like this so that it is the very same thing as x. Okay, so the cube root of x cubed is just x, right? Now, what is the point in doing this? Well, remember the recall? I now have a difference of cube, where the inside of this bracket is my a, and the inside of that bracket is my b. Take a look. This is a cube minus b cube. Yeah? So my a is the inside of the bracket, which is the cube root of x plus h. So I'm going to apply that formula over here. Pretty simply, what am I going to get? A minus b, cube root of x plus h minus b cube root of x times a squared plus ab plus b squared. So a squared, the cube root of x plus h squared. Let's put the bracket here and a square bracket there. Plus ab, the cube root of x plus h times the cube root of x. Plus b squared, the cube root of x squared. And let us close the square bracket. How can I rewrite this so it's a little more elegant? Well, cube root of x plus h minus cube root of x times cube root power 2. I know my rules of exponents, and so do you. This is the same as x plus h to the 2/3 plus x plus h to the 1/3 times x to the 1/3 plus x to the 2/3. And that is the end of my aside. I am done playing algebraically with this expression. I am now ready to go back here and replace this h by basically this h, because after all of this is equal to h, right? All of this is the same thing as h. So here we go. This will be the cube root of x plus h minus the cube root of x over all this which is h. So cube root, I'm going to have to write small because I need to squeeze that in. So this times the second part of the bracket, x plus h to the 2/3 plus x plus h to the 1/3 x to the 1/3 plus x to the 2/3. Wow. Why all this? In order for us to get a simplification. I'm sure you can see it. Where is the simplification? Right here. All of that is gone with all of that. So that is no small thing gone. This is now the limit as h goes to 0 of 1 over, here we go, x plus h to the 2/3 plus x plus h to the 1/3 x to the 1/3 plus x to the 2/3. I can extend my division bar here. Wow, nasty expression. What is that equal to? Time to cheat, really. Time to replace h by 0. So that is 1 over x plus 0, so x to the 2/3 plus x plus 0, that's x to the 1/3. What's x to the 1/3 times x to the 1/3? It's x to the 2/3 again. Plus x to the 2/3, look at that. We have here 1 over 3x to the 2/3. All of this to actually find what? The derivative of this function. F of x is equal to the cube root of x. Wow, that's pretty insane. So I'm going to erase this. Just use my result to answer the question. Is f of x differentiable at x is equal to 0? So let me erase this in 2, 1, 0. So is f of x, So is f of x equals to the cube root of x differentiable at x is equal to 0 is the question we need to answer. We have found that f prime of x is here, 1 over 3 x to the 2/3, which you can of course rewrite as 3 cube root of x squared. So what is f prime of 0 now? What is f prime of 0 now? Well, just replace 0 into that, and guess what? Guess what? This is 1 over 0. dne. So in other words, f of x is not. So in other words, f of x, in this case, the cube root of x, is not differentiable. That simply means its derivative does not exist. Differentiable at 0. Now, graphically, what does that mean? Graphically, what is the graph of f of x is equal to the cube root of x? Well, it's going to look like this, more or less. If you don't know, give yourself a table of values. Take intelligent values of x's. For example, -8, -1, 0, 1, and 8. Because the cube root of -8 is what? What's a cube root of -8? What number times itself will actually give you -8? The answer is -2. -2 times -2 times -2 is -8. Alors, -2. What number multiplied by itself 3 times will give me -1? Cube root of 0, cube root of 1, and cube root of 8. What does that give me in terms of a graph? Well, -8 minus 2 is about here. -1, -1, 0, 0, 1, 1, 8, 2. This is a weird graph, baby. This is a weird graph. It's going to look like this. It's going to look like this. Wow! Like that. And I am actually interested in finding out what is happening at 0. So it's the behavior of the function in that area that I am concerned with. So I'm going to zoom in. Zoom in. What is it that I have here? I have something like this. It's not very, very good, but I think you get the idea. Now, you remember that the derivative is nothing else, graphically, than the slope of the tangent line. So if I take a tangent line here, I'm going to get that. If I take a tangent line here, I'm going to get that. And at some point here, the tangent line is going to be absolutely vertical. Because look at this thing going steep, 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 and then flattening out again. So what do we have here? We have that when x is equal to 0, f of x equals to the cube root of x has a vertical tangent line. And as you know, the slope of any vertical line is what? dne. Hence, the slope of the tangent line does not exist, i.e. f prime of 0 does not exist. If you recall the previous example, when x was 0, we had an asymptote. We had a discontinuity. Here we don't. This graph is very nice. It's very continuous, except that it behaves weirdly at 0 because it has this really vertical tangent line. So that's a second reason why we're going to encounter points of non-differentiability when we have vertical tangent lines. Finally, there is a third case that I will investigate with you in 2.1.0. So consider now a function that we have met before. We have reviewed it in our review videos, and we know it under the name of root x. So this is, I guess, my second example. Consider f of x is equal to, did I say root x? I'm sorry, I meant absolute value of x, not root x. F of x is the absolute value of x. Is f prime of x differentiable? Is f prime of x differentiable at 0? Okay, so basically what am I asking? Does the derivative exist when x is 0? The derivative is the slope of the tangent line. So graphically, this is a weird graph, right? But before we actually look at the graph, let us calculate the derivative. F prime of x. Okay, we have two ways of expressing this. Yes, we have limit h goes to 0, fx plus h minus fx over h. We said that this was going to be the way that we actually use the most often, and we're going to stick to that. There's also another way. We saw in the second video on derivatives. It is this one. F prime at a is the limit as x approaches a of f of x minus f of a over x minus a. Right? For this function, it's going to be slightly more convenient to use the second one. So I'm going to use this one instead of the first one, exceptionally. Usually I like this one a lot, but for this example I'm going to use that one. So f prime of 0 is going to be the limit as x approaches 0 of f of x minus f of 0 over x minus 0. That means that there are scratches on my whiteboard. That means that this is the limit as x approaches 0. F of x, valeur absolue, absolute value. F of 0, 0, absolute value of 0. So this is the guy. I got to figure this out. Are you surprised to actually get 0 over 0 when you plug that in? No, it happens all the time. Now, how do I evaluate this? Wow, absolute value. Unless I remember the definition of the absolute value, then I'm going to be stuck. But I remember the definition, yes? Absolute value is itself if x is greater than 0, and it's minus x if x is less than 0. We could put the equal sign anywhere, put it here for the sake of the argument. So, according to what we have here, we need to do what? We need to investigate the limit as x approaches 0 of the absolute value of x over x. That, mesdames et messieurs, requires a left and a right limit. So limit as x approaches 0 from the right, or say from the left here, and then we're going to have the limit as x approaches 0 from the right over there. Usually we do the left and then we do the right, of absolute value of x over x. What is that? Here we are on the left of 0. You know what that means? We are less than 0. If we are less than 0, I can replace the absolute value by minus x. So this is equal to the limit as x approaches 0 of minus x over x. The x's cancel and I get minus 1. Over here, I am on the right of 0. That means that I am greater than 0. That means that I can replace the absolute value of x just by x. And x over x is 1. What do I conclude? I have here that the left limit and the right limit are not the same. These are not equal to each other. What does that mean if the left and the right do not equal to each other? It means that the limit as x approaches 0 of the absolute value of x over x does not exist. And in turn, because this limit does not exist, remember what this limit was f prime of 0. So that implies that f prime of 0 does not exist, and that implies that f is not differentiable at x is equal to 0. Very nice. Let's just consider, for our last conclusion on this, let's consider the graph of the absolute value of x. So erasing this in 2, 1, 0. Just to conclude this little video on differentiability. So conclusion, f of x equals the absolute value of x is simply not differentiable when x is 0. And look at the graph. Look at the graph. The graph of the absolute value is well known, yes? The graph of the absolute value is well known. It's the old V centered, this one is centered at the origin, yes? Oh boy, that it does not look like a straight line, huh? All right, so can you see it? It's a little pale. So yeah, it's actually very pale. We can do better. All right, here's the orange and green V of the absolute value right here. Notice that right here, at the point we have an interest for, at x is equal to 0, something pretty strange happens. Yes, here, the line goes there and then hooks up completely to the left here. Right there, you have a slope that is negative. And right here, you have a slope that is positive. And there is no smooth change in here. It comes to 0 and abruptly moves in the other direction, right? So what we have here, 0, is called a sharp edge, or more technically, a cusp, right? A cusp is actually a sharp edge where the curve changes direction very abruptly, where there is an abrupt change in direction for this curve, right? So that is the third condition, if you want, for which we are going to encounter a point of non-differentiability. So summary. Let us actually try to see if we can put together what we've learned today. So f of x is not differentiable. Such an important word. I want to put it in capital letters. Is not differentiable. Not differentiable at x equals a if one of the things that can actually happen is the first example we saw today, the graph of 1 over x, it had an asymptote. If f has just like put like a asymptote simply. It's vertical, but it's understood. An asymptote at x equals a. The second that we saw, it was the graph of the cube root of x, where when we sketch it, we end up with a vertical tangent line. Wow. Has a vertical tangent line at x equals a. right? So, oh, by the way, yes, on the first one, f of x has an asymptote, and asymptote means what? What do we correlate asymptote to? Discontinuity, right? Discontinuity, right? So discontinuity in the form of an asymptote results in a point of non-differentiability. Finalement, what? F of x has a cusp, a sharp point, a sharp edge, we said, at x equals a. These are the things we actually encounter the most in order to figure out if a function has a derivative at a point. Good, enough for one day. I will see you for the rest later. Have a good rest of the day.